So the next example we'll do will be this one. So y double prime equals y. Again, this is something that we could have done earlier. This is a pretty straightforward chapter 4 problem. And what we're going to do is we're going to pretend that we have a power series solution y and then figure out what that power series is. So we're going to do exactly like we did before. Write y as this power series, c sub n x to the n. Sum goes from n equals 0 to infinity. If we differentiate once, we're going to end up with the sum from 1 to infinity of c sub n times n x to the n minus 1. And if we differentiate again, y double prime is going to be the sum starting at 2 going to infinity, c sub n times n minus 1 x to the n minus 2. And then we're going to take y double prime and y and plug them back into our differential equation. And so this tells us that this bottom sum, the sum starting at 2, going from 2 to infinity, c sub n times n minus 1, x to the n minus 2, is equal to the sum of the original function y, which is the sum from 0 to infinity, c sub n x to the n. Now we don't have to do anything with the right-hand side. The left-hand side, we're going to shift the index by 2. So I want to lower the starting value of our sum, which means that I'm going to change all my n's to n plus 2's. Okay, so we have to add we have to add 2 to each of these n values. So this is going to be the sum starting at 0, c sub n plus 2 times n plus 2. So if we take n minus 1 and add 2 to it, we'll get n plus 1. And then x to the n minus 2 will be x to the n. That's equal to that. By the way, I knew that I needed to shift by 2, mainly because I needed this x to the n minus 2 to be the same as x to the n. It also worked out that that's our starting index and everything works out fine. It will not work out so nicely in general. Okay, so we'll talk about an example where things do not work out so nicely. We'll do one next, actually. But in this case, everything did work out nicely. And so now all we have to do is we're going to use the fact that if we have two power series representations, then if they're equal, then the corresponding sequences are equal. And therefore, we get that c sub n plus 2 times n plus 2 times n plus 1 is equal to c sub n. And this is true for all values n greater than or equal to 0. And we use 0 because that's the starting place for the sum. That's the starting index. And so this tells us that c sub n plus 2 is equal to c sub n over n plus 2 times n plus 1. Okay, and so this is what we have. Now, notice that this is c sub n plus 2, meaning that the first two values need to be defined. So this can only make sense when n is greater than or equal to 0. And so the smallest value that this can be is c sub 2. So c sub 0 and c sub 1 we need to have constants for, which, if you think about it for just a second, makes perfect sense. This is a second order differential equation. We need two constants, right? So hopefully that is a reasonable thing. So let's call C0 A and C1, we're going to call it B. And then C2 is going to be what happens when we plug in n equals 0. So C2 is going to be the value 2 terms back, so C0 over 2 times 1. So over 2 times 1. So this is A over 2 times 1. And again, just for the first ones, I'm not going to worry about simplifying because it's going to be easier to spot the pattern if all the values are in there. C3 is going to be 2 terms back, so that's C1 over 3 times 2. So that's B over 3 times 2. C4 is going to be C2, which is A over 2 times 1. And then we're going to divide by 4 times 3. So times 4 times 3. And then maybe one more. C5 is going to be C3 divided by 5 times 4. So it's going to be B divided by 5 times 4 times 3 times 2. And of course, what's going to happen here is that the even terms, C sub 2n, is going to be A over 2n factorial. Okay, so C sub 4 is A over 4 factorial, C sub 2 is A over 2 factorial, C sub 10 would be A over 10 factorial, and so on. And C sub 2n plus 1 is going to be B over 2n plus 1 factorial. And so here we have even and odd terms. So I'll show you how to handle that. So what we're going to do is we're going to take our power series. So we'll put a pin in this. We'll come back to this sequence here. But we have y, which is the sum of c sub n x to the n, as n goes from 0 to infinity. What we're going to do is we're going to write the even and the odd term. So here's the way I like to think about it. And I'm going to write out the details, at least for the first time. C0 plus C1x plus C2x squared. This is our power series representation. C3x cubed, C4x to the fourth. Let me do one more. C5 x to the fifth, and so on. Okay, so this is our power series representation. Okay, this was C. I don't want to squeeze that much in. This is C5 x to the 5, and so on. Now what we're going to do is, since we're inside the interval of convergence and everything converges, I'm going to separate the even and the odd terms. So this is going to be C0 plus C2x squared plus C4x to the fourth, and so on, plus the odd term C1x plus C3x cubed plus C5x to the 5, and so on. Okay, so that's our value y. And what this is, if you think about it, is this is going to be the sum of c sub 2n x to the 2n, right? You have the even terms plus the odd terms. It's the sum from 0 to infinity, c sub 2n plus 1 x to the 2n plus 1. Okay, so I just wanted to explain the jump between this power series. Okay, so we have c sub n x to the n, and you can break it into the even and the odd terms. So that's really all you're doing is you write it out, you group the even terms and the odd terms together. When I say even and odd, what I mean is terms with even exponents, terms with odd exponents. It turns out that this function is an even function and this function is an odd function, but that's not actually what I mean. I just mean the terms with the even powers. Okay, so 0, 2, 4, and then the odd powers 1, 3, 5, and so on. Now, what we're ready to do is we're ready to go back and we're ready to plug in what we had for our expressions for the even and odd terms of our power series, okay, for the sequence. So c sub 2n, the even terms, turns out to be, this is the sum from 0 to infinity of a over the quantity 2n factorial x to the 2n. So our c sub 2n was this a over 2n, and that's what goes here. Plus we'll have the odd terms, which would be the sum starting at 0 to infinity, b over the quantity 2n plus 1 factorial x to the 2n plus 1. Okay, and again, now it's up to us to recognize these power series. This is a times cosh of x plus b times sinh of x. And of course, hyperbolic cosine and hyperbolic sine are defined as sums of exponentials. So if you wanted to, you could write cosh as e to the x plus e to the negative x over 2, plus sinh is e to the x minus e to the negative x over 2. Okay, and then it works out that you can actually distribute the a, you can separate all the terms. You get e to the x terms, e to the negative x terms, and you get some constant times e to the x plus another constant times e to the negative x, which is, if you think about it, what we should have known about 10 minutes ago, because this involves solving the characteristic equation r squared equals 1, which has solutions r equals plus or minus 1, and therefore your solutions are c1 e to the 1x plus c2 e to the negative 1x, right? So this is the better way to do it, but hopefully with power series, this introduces the idea, and these are not too painful of examples.